E direi di passare alla prossima presentazione. Shiftiamo adesso all'inglese, so now we move to English. Let me introduce Professor John Campbell, even if I don't think he needs any introduction, but let me do my job, Professor. And we are curious to understand now how to solve the problem of casting that, as we discovered yesterday, are more than we supposed to have. So thank you, and you have your 20 minutes.
Okay, thank you. Well, good afternoon once again. And those of you who were in my previous lecture yesterday will remember that the surface could fold over and we get a double film which acts as a crack in the liquid. I call this a bifilm. And you remember that the other major damaging feature was when this folded in with a lump of air. And this I called a bubble. Okay? So very simple. So most of our casting systems, like you see here,
But now we move the presentation with the up and down.
How do I get that?
Okay.
Thank you. You see, most of our casting systems, direct pour, or even bottom gating, because of that cone, we're taking in air into the system. And huge quantities of air, masses of air, are going down into our running systems. There's more air than metal. So it's not surprising we have porosity in the castings. The castings are full of air, plus oxides. Now, if we have an air bubble in the casting, you may say, what's the problem? Because the air bubble can float out, arise at the top, burst, gone. So what's the problem? The problem is this, that the air bubble has air inside, so you know that it has an oxide skin. And now the question is, how does it rise? That's not straightforward. It can only rise if it has enough buoyancy, force, to break the oxide, and so as the oxide splits and moves, the bubble can move up a little, but immediately the oxide reforms. And so it splits and reforms, splits and reforms. And what you can see happening is that the oxide skin on the bubble flows around the bubble, comes together under the bubble, dry side to dry side, always dry side to dry side. This is a fundamental issue in the whole of bifilm technology. It comes together, so there's no bonding now, and that goes back through the system, all the way down through the gate of the casting, along the runner, up the screw, probably about halfway up the screw, the point where the air was first entrained. So now we have this bubble trail, and the bubble goes up, leaves this long trail as a long crack. So now you have cracks in the casting, probably 1 meter long, from one bubble. Now, you can see that we put hundreds of bubbles into the casting. So now we have hundreds of cracks, meters long. So, and maybe thousands of cracks. I mean, if we had making a big casting, no wonder we have quality problems. It's unbelievable. Now, so in my view, although the bifilm is a bad defect to have because it's a crack which you don't know is there. It's too thin, you can't see it. So this is an evil thing to have in your casting, and you will have thousands or millions in your casting. But the bubble is even worse, because the bubble makes a bifilm crack 1 meter long every time, or depending on how big your casting is. So it's essential to get rid of the bubbles. And in the new thinking, for the new running systems, this was my priority. We had to bring the speed down to below 0.5 meter a second. You all know my 0.5 meter a second. This is the speed at which the metal doesn't jump to fold over on itself and fold in its oxide. So if it's below 0.5 meter a second, you can't make bifilms. And so bifilms is easy to deal with. The 0.5 meter a second is fairly easy to do. But the bubbles was difficult. But now we have a solution. So if I can find out how to work this machine, here we are. Ah, wonderful. Maybe I can escape now and
Open.
Okay, I have it. This is a water model showing a conical basin and showing how we take air into the system. So here we've got 2 ingates, the metal's coming in. At the moment we'll have a look at, here is the nozzle from the basin, here's the metal going to the conical nozzle, and look at the metal falling and all that air churning away. And here's all the bubbles coming up. You can see why our steel makers completely fail to make good steel now. All the business of clean steel fails at this point. Nobody's dealing with this point, but this is the most important. It's entrainment which is important, not detrainment. Everybody's working on detrainment, on launders. Forget it. The problem should never have been there and can only be controlled by the casting process. It's the casting process which is critical. Okay, let's get out of this. Okay, I think I'm winning. Yes, so one of the ways of doing it is the offset step basin, so that it's here the bubbles can detrain by coming up this way. The metal goes down, but unfortunately this process also introduces bifilms at this point, and they go down. So it's not a good system, and it's not as good as the contact pour system, but it's not bad. And this is what we're aiming for. You remember, we want to break the surface film as we fill a mold, and so the surface oxide becomes the skin of the casting. You all know that. And here is a situation where now we're doing, don't take any notice of this at the top, but we're filling, we're doing bottom filling, which is all the right thing to do, but now we're coming in at the wrong speed. And of course, this is like quicksilver. Your liquid steel or your liquid aluminium behaves like quicksilver, and so you lose almost no speed around this corner, and so you get, it jumps the full height of the casting. And you can see this, particularly in steel foundries. You watch the metal come up and it tumbles down. And so this is a wonderful system for creating bifilms and getting the worst possible properties. Okay? So if we move on and we say we put on a small offshoot here, it does a little, it helps a little, but it's nearly useless. And if we move on to a vortex gate, you remember some years ago, about back in 2011 or 2012, I thought about the vortex gate. And it is a wonderful gate for reducing speed, because the metal can come in, hurtles around the gate, but it now moves up at the speed, which is the ratio of the area coming in to the area going out. Simple system. So easily you get 10-to-1 reduction. So 5 meters a second coming in, half a meter a second going up. Perfect. What could be better? It was terrible. And the reason for it being really bad was that the bubbles were centrifuged into the center and they couldn't escape. And so they were definitely, every bubble in the system went through into the casting and ruined the casting. Useless, okay? Now, the bubbles were the big problem. So there was that beautiful gating system ruined because it couldn't deal with bubbles. So, we can... I seem to be having problems. Oh, here we are. Here is our first attempt to put in what I call a flush filter. Now, I'll have to describe this in some detail later. But if this is my runner, normally we would put a gate on here, a filter, and then the casting. And that was completely the wrong way to do it. Because bubbles arrived, they would go up the gate, they would sit under the filter, and what we know from our X-ray video studies is that, first of all, a small bubble arrives under the filter and just sits under the filter. It hasn't enough buoyancy to push through. But then another bubble arrives, and now it becomes twice as big and twice as much buoyancy force. And then another, and then another, and finally the whole surface of the filter is covered with a bubble. And now it has the full pressure of the system behind it. And now it goes bloop, and the great bubble goes through and up and makes a hell of a mess of the casting. Okay? And then the next bubble gathers, and slowly, slowly, slowly it builds up, and then bloop, and then off again. And so these huge bubbles, which now go through the system, make a massive bubble trail as a massive crack through the casting. So maybe you only have half a dozen cracks through the casting, but they're from the bottom of the casting to the top. And you can't get at them to dress them out. The casting is ruined. Okay. Now, so the reason why this system didn't work too well is that it's been built in the computer, of course, with the refractory tube systems, which never work properly. I would never use a refractory tube system in my steel foundry. I would throw out all the tubes. I think they're bad news for good castings. So, oh, here we are. This was the system now in which we have what I call a flush filter. Remember, we have our runner here, and on this end I have what I call a spinner, where I take metal away and spin it around, and what's interesting about that is it slowly builds up a back pressure. As the spinner rises and the metal goes and gets higher and higher, you're building up your back pressure in this runner. And here, instead of the gate coming off and the filter being here, we put the filter here, right on the runner. And now the bubbles arrive. They try to sit under the filter, but now the bubbles can escape. And now once the bubble gets into the spinner, they're centrifuged into the middle of it, and they can't get back into the system. If you don't have a spinner, but you have a rectangular system, most dross traps are rectangular. The metal comes in, hurtles around the dross trap, all the dross and all the bubbles come out and straight up the next ingate, which you don't want. The spinner is very clever and very important. It takes the defects into its center and can't reverse back into the runner. So that's a very important part of the system. Plus, it gradually gives a pressure back to the filter and gradually puts the metal through the filter. So the metal comes through now very slowly, because it only has a small head. And as this head builds up, so we build up our level way below our ½ meter a second. And now we can fill the base of the casting slowly, but then now the spinner fills to the top. And now we get our full pressure now from our sprue, and now that comes through full speed and the casting fills up at full speed, so we lose almost no seconds, maybe 1 or 2 seconds for the filling of the spinner and the filling of the gate, and then we come up to full speed and we fill the rest of the casting in whatever it is. So the new system is a flush filter system to allow the bubbles past, and a system over here to catch the bubbles and not bring them back again. So the elimination of bubbles is the most important thing in the whole of the casting, a new casting technology. And it's a simple idea, but it makes a huge difference to the casting. The other huge difference is the contact pore. And you remember our 3 images we had here. The contact pore again stops bubbles coming in right at the front of the system. And that is another marvelous introduction, and it would be the way I would, if I were going to make a foundry, that's what I would do. I'd put contact pouring in every time. Unless I were to go to counter-gravity. And counter-gravity is something sent from heaven itself, you know, especially for foundrymen, if they can do it. And mostly it's rather difficult to do, but for all you lucky people casting aluminium, it's okay, you can do it easily. The rest of us are going to have to struggle. But I'm beginning to see how irons and steels could be counter-gravity filled, and there I think is a big hope, a big white hope for the future. So quickly now, if we move on. Well, I would move on if I could. Here we are. Here are our systems. For the first time in my history, I can now put a good running system onto a 2-part mold. All my previous running systems had to be 3-part molds, had to come under the mold to come up. For the first time, I can do it just on a, here's our runner, which is this thing along here. We've got 3 gates, we've got 3 filters, which are sitting flush, but this time they're not sitting on the top, they're sitting to the side. It's just no problem. The important thing is, whether it sits here or here, it's flush. It's so the bubbles can keep moving and get out of the way. So here we're actually got a gate which is coming up and then coming in at the side, which is a nice system. Here we can actually come in underneath the casting if it's all in the coat. Here, if there's some in the top and some in the bottom, we can come in the bottom fairly well. And maybe we can come in at the full depth of the runner. If we've got a lot more down here in our drag, then the system starts to fail. Then you need a 3-part mold, which is, okay, there's nothing for it. You have to grit your teeth and put up with the expense. But this, I'm happy this system works well, and let's move on using this. Yeah, and so this is one system in a 3-part mold in which metal comes down. Here we've got the filter at the side of the runner. Here it is. So here is the runner, here's the filter, here's the gate. See, this is very simple to mould, and nothing in the base part, just a flat piece of sand. A very simple system, but works beautifully. And notice again the spinner here, collecting the bubbles in the centre. And you need a vent from the spinner. Oh, I'm being told by Madam Chairman that I'm about to run out of time. So, and here's another system in which, again, we've got the flush filters, but now we've got some, we've got the runner in the base part. But as I say, these are just simple systems. And thank you.
Thank you very much for your speech. Is there any question? No one has question. I have one, if I can. As far as we got I say our, I'm not a foundryman, but I study a lot them. Castings are full of defects. I mean, big defects of oxide. And porosity we can see easily, but these oxide are quite small as far as I got. So, yeah. And how can we recognize them? And do you have an idea about the improvement in terms of, let's say, percentage of properties increased when we avoid, if we are able to?
These are wonderful questions, thank you. Normally, when you cut your casting, you polish it, look at it under the microscope, it's not possible to see the bifilms. However, what you can see very often are inclusions sitting at grain boundaries, only sitting at some grain boundaries, okay? And those are the grain boundaries which have a bifilm in them, okay? Because what I think is, inclusions don't precipitate at grain boundaries, I think. They only precipitate on bifilms. They always sit on the outside. You remember, the inside and the top surface is dry, the bottom surface is in atomic contact. Now the bifilm has surfaces in atomic contact, but are cracked down the middle. And so when steel people talk about, oh, we've got brittle carbides at the grain boundaries, this is rubbish. The carbides are ductile. They appear to be cracked because they've got a bifilm down the middle. Okay? So those boundaries that have bifilms, and a big percentage of the bifilms will be at boundaries, and that's because they're pushed by the growing grains, and then they meet another grain growing this way. They automatically finish in the grain boundaries. Some don't finish at the grain boundaries, they go transversely, but many sit there. And so nearly all our grain boundary precipitates, they're nearly all cracked. And the cracks are nothing to do with the brittleness. They're all ductile materials and they're strong and crack resistant. The cracks are bifilms. So then you can see them. Okay.
And do you have an idea about
and the brazing properties? Maybe a factor of 10. Okay? It's not trivial. We're not talking about a 10% increase in properties. I think we're talking, sometimes we're going to be talking 10 times.
Wow.
10 times. And, I mean, this is truly terribly important. And the industries must know this. I mean, it's so important to get this information out. And at the moment, we're making rubbish materials and spending our lives working hard to make bad castings. When I think it's actually rather easy to make good castings, and I think the results will be fantastic. We do have to start with well melted and prepared metal, because there's lots of bifilms before we start casting, because someone else has cast our metal before, so they've already filled it with defects before we pour it, and we have to get those out. And that's another story. We haven't got time for that today.
Thank you so much.
Okay.
Thank you again.